Hello, I'm Charles Fox. I'm a senior lecturer at the University of Lincoln. I study robotics and autonomous systems, and today I'm going to tell you about some of my work in agricultural robotics. This slide shows three of the robotic systems I've been working on recently. The one on the top left is called Ibex. It's a robot which drives around grassland farms, so dairy sheep farms, looking for weeds like stinging nettles and dot leaves, and targeting them with precision spray. The one on the top right is from a project called Arwac. This is working in arable crops. It's looking for a different kind of weed called blackgrass, and it's trying to hoe it out from in between fields of wheat. And the one at the bottom is from a project called Laserboom. Again, we are spraying crops, in this case, here from a large tractor-sized vehicle. And in this project, we're controlling the arms of the boom sprayer. We're moving them up and down to optimize how the chemical gets sprayed across the field. Why do we do this? Why work on agricultural robotics at all? Like many research areas today, it is all driven by the concept of sustainability. Most people now are much more aware of their environment than they used to be. Most people are aware that we live on this small ball of rock called the planet Earth. When you look at it from far away, you can see how vulnerable it looks. And if this system goes out of balance, things could go very wrong indeed. So by sustainability, we mean trying to create systems, engineering, economic systems, which keep the world in balance. We don't want to be outputting too much nasty chemicals. We don't want to be using up too many resources. We want to try and leave the world in the same kind of state that we found it in, which is roughly what my old granddad used to say. He used to farm with horses back in the day, and a good farmer should basically leave the farm in the same or better state than he found it in. So sustainability is all about balance. It's all about not having too much of things and not running out of other things. So right now, we are producing too much of these things, possibly people. The human population continues to grow. It is projected to rise by around 25% by 2050. And unless we do something, that's going to result roughly in people fighting each other for resources, or it's going to require the population to be controlled in some other way. Or we could have the population grow and actually be able to feed them. Now that's going to require producing more food for these people. We are currently producing too much CO2. This is responsible for human-caused climate change, according to our climatologist colleagues. And they tell us that we need to reduce fuel consumption. We need to burn less fossil fuels, which are outputting that. We're also outputting too many chemicals as a side effect of agriculture. This includes herbicides, pesticides, fertilizers. All these chemicals are intended to land on the crops to do something useful and agricultural, but many of those chemicals don't end up in the crop. They run off the crop, and they end up in the rivers, and then they end up in the water system. In some cases, where people can drink the water. And some of those chemicals are known to be carcinogenic, meaning they can cause cancer. And so we'd like to stop outputting chemicals into those places. On the other side of the equation, we are running out of certain things. Fossil fuels are a limited resource. They were laid down around the time of the dinosaurs, and when they're gone, they're gone. And much of recent agriculture has been driven on the assumption that fuel is an unlimited resource. We've seen our tractors getting bigger and bigger, for example, like in this figure. Fuel is increasingly a resource that people have to fight over in places like the Middle East, where we dig it out of the ground. Less obviously, we are running out of herbicides. These are the chemicals that kill the weeds. Not so much in the sense of running out of their chemical components, but we're running out of their ability to work. And that's because plants, including weeds, continue to evolve. And every time you create a new herbicide, nature will find a way. It will try out many different evolutionary steps. And if one of those steps manages to evade your herbicide, then the plants with those genetics will reproduce, they will prosper, and before you know it, in some cases very quickly, in a matter of years, they will have taken over the whole weed population. We're also running out of herbicides in the sense that we find out more and more often that they are harmful to humans. So, for example, glyphosate or Roundup, that's the stuff you put on your garden patio, has an increasing amount of evidence building up that it may cause cancer in humans, and so many countries are starting to ban those chemicals. That means we don't have access to them in agriculture anymore. We're going to run out of space for growing food if we have to start producing biofuels. When my granddad was a farmer, he used to devote about a quarter of his farm to growing fuel for the horses to eat. And that's how you powered your machinery in those days. And we may have to go back to something like that if we devote part of our farms to growing biodiesel to make the tractors work and other vehicles. But if we do that, there's less space available to grow the actual food. There is some space still around doing nothing or very little. If you go out into the moorlands, out into the national parks, these are terrains which have not historically been any use for agriculture, but maybe there are ways to bring them into use in suitably sustainable ways. We're running out of fertilizer. I went down a potash mine a few years ago near Whitby, and potash is used for agricultural fertilizers after some chemical processing. And potash is a limited resource. These guys have been digging their mine, I think, for many decades, but it's getting harder and harder for them to extract. And when you walk around that mine, you can see where they've been, you can see where they've taken it all out of the easy places, and you can see where they're mining now. And it's getting harder and it's getting more dangerous. They're starting to have to mine underneath the sea, and in places where if the ceiling falls in, it can endanger the lives of the humans who are working down there. And finally, we've been running out of diversity for some time. Big agriculture has pushed us towards a world of monocrops, where farmers are incentivized just to grow not even one crop, but one variety, one genetic version of a crop. And there's a danger that if we cover the whole country in one specific type of wheat, if anything goes wrong, if there's a disease that appears affecting that variety, then the whole system could fail. So it's important for sustainability and for managing the risk in our food systems that we have more diversity. We need to be growing many different things so that if something goes wrong with one, we have some kind of a backup plan. So the population is rising. We need to feed more people. Is there enough food to feed them? Actually, there is already, because around 40% of food is not actually eaten. So part of this is just to do with fussy consumers, people throwing things out of their fridge when they're still perfectly edible. Part of it is to do with them being picky in the supermarkets, only picking vegetables which look nice and avoiding what is called wonky veg, anything that isn't immediately attractive to them. Some food is lost in the supply chain. That means moving food around, storing it, transporting it on lorries. But much of it is lost during the agricultural process itself. And the word agriculture comes from the same root as the word aggregation. And aggregation means doing things in bulk. So we didn't always do farming in bulk. We used to do what is now called horticulture, and horticulture means tending to plants individually as humans. So if we look at these ancient Egyptians over here, we can see these Egyptian slaves probably are working with manual tools out in the fields, but they're working with each plant as an individual. And if you do that with humans, you can give each plant the optimal combination of food, fertilizers, water, and you can harvest it at the right time. You can look after it, monitor it for diseases, and generally care for each plant like a gardener would do today. Of course, that was easy in Egyptian times because the cost of human labor was basically free, because Pharaoh had a bunch of slaves to do this. You had to pay them in a bit of food, but otherwise you don't have what are now called labor costs. And a major driver of tractors getting bigger and bigger in the fields today is labor costs. If you make your tractor twice as big, it costs you half as much money to pay someone to drive it up and down the field at £10 per hour. So there's a few people today who try and do their farming more like the Egyptians used to do. These people are called hippies. Here's a picture of them on the right. And many people enjoy being part of nature, part of ecology in this way, try to grow food in a more sustainable way. But it isn't cost effective to do that unless you're doing it for fun or for your own philosophical, ecological purposes. There's no way we could feed everyone in this way. So I work in robotics, and my interest is in trying to do something like that, but without using the humans. By using small agricultural robotics, we can try and move away from big agriculture back towards per plant horticulture. Okay, remember, horticulture means looking at each plant as an individual and looking after it. There are many reasons then to work on this right now. Part of it is to do with these balances of resources, population versus environment. Here in the UK, we have some specific labour issues. One of them is to do with farmers getting older. The average farmer here is about 65 now. Many young people don't want to go into agriculture. And at least until very recently, we have therefore been relying on cheap immigrant labour from the European Union, most of which has now gone home because we told them to go home. So currently we have many agricultural crops are just not being looked after because there's no one to do the work. For example, there are fields and polytunnels full of strawberries with no one to pick them. And many of those fruits have just been left to rot because it wasn't cost effective for anyone to pick them. British citizens usually don't want to work for a wage which is comparable to what the same citizens are willing to pay for the food product. So the idea of a small robot then is to get away from aggregation and bulk processing and to try to use intelligence, artificial intelligence, machine learning, to behave more in the manner of a human horticulturalist, to try and work with individual plants and to apply only the resources that are needed. So rather than bulk spraying a whole field full of chemical, if the chemical is only needed on 3 particular plants, we'll just go and put small blobs of chemical at only the places where it's needed. And then the rest of it doesn't blow away in the wind and end up in the river. I work in Lincoln as part of the University of Lincoln and also as part of a collaboration called the CDT, Centre for Doctoral Training in Agri-Robotics. So we work very closely with the University of Cambridge and the University of East Anglia. And these 3 universities together form a triangle, a geographical triangle, which I like to think of as the Silicon Valley of agriculture. This triangle hosts many of the most innovative types of agriculture in the UK, and it hosts many of the companies who make the machinery to power that agriculture, and it hosts these 3 universities who are collaborating with each other and with those companies to try out lots of new technological innovations. So when scientists talk about the Golden Triangle, they usually refer to the area between Cambridge and Oxford and London, which has traditionally hosted many scientific experiments and been given most of the funding for those experiments in the UK. But when we do agriculture, and especially agricultural robotics, the Golden Triangle is right here. Here's what Lincoln looks like. It has some very beautiful places. It has a famous old cathedral. This lower right image is hosting much of our agricultural robotics work. The lower left image is the former home of George Boole, who was one of the pioneers of computer science. George Boole invented what is now called Boolean logic, and that's what's used to create logic gates, and those are used to make microchips, and those are used to build all of our computers, and that all came from here in Lincoln. So I'll talk a little bit about some particular projects I've recently been involved in. There are many others here in Lincoln. These are the ones I've worked on. Other people within that Golden Triangle work on many other things as well. So the first one I'll talk about is called Ibex, and this is the robot for grassland weed spraying. So this means stinging nettles, dock leaves, thistles on dairy farms and sheep farms. These are traditionally controlled in 2 ways. One is you blanket spray the whole field with what is called a selective herbicide, and that's an expensive chemical which has been created by chemists to only kill the weeds and to leave the grass alone. The other way to do it is to use what is called a generic herbicide. That's a chemical that kills every kind of plant. And to do this, you typically put a backpack on your own back and you go around with a spray stick and you manually look for the weeds and you spray each individual weed. And that's done usually with a chemical called glyphosate, otherwise known as Roundup when you buy it in the supermarket. That's the same chemical that you put on your patio to control your weeds at home. So the bulk option is expensive and it's bad for the environment, chucking so much chemical across an entire field. We prefer this precision process, but even with the precision process, you've got to pay labor costs. You've got to pay someone £10 an hour to walk around a field looking at weeds, which isn't much fun. And it's also probably dangerous because we now know that chemical very likely causes cancer. And indeed, it has been banned in several countries. So there's a need to find new ways of controlling these weeds in the grassland. I'm just going to share my screen for one moment, and I'll show you some parts of the solution that we have been developing. me one moment to come and share my screen. Okay, so this was an early version of the Ibex robot. It's based on a former bomb disposal vehicle used by the police. And in this early video, we were considering how you swathe a field. So swathing means driving up and down, like when you mow your lawn, so that you cover every square meter of the field. There are different mathematical algorithms you can use to figure out how to do your swathing. It's easy if your field is a square, like this garden. So when we started building this, we were just testing it in my garden. After that, we went on to bigger fields. For a basic square, you've just got to drive up and down, just like a lawnmower, until you hit an obstacle, like this chair. So when we detect a chair, and in this case, we've got a laser scanner or LiDAR mounted on the front of that vehicle. When you detect a chair or another obstacle, you have to replan and find a new way of swathing the field. You can see there's a bunch of other sensors mounted on the robot as well. Some of these are doing GPS, some of them are doing what is called inertial measurement. That means figuring out which way you're rotating, which way you're heading. And there's some visual sensors as well, which will end up getting used for recognizing the weeds. So this Ibex robot evolved through several iterations. We also added a spray system to that platform. We enhanced the machine vision to start doing individual weed recognition. And I'm just going to find you some video of that as well. Screen. Okay, so in an image like this is just a still image taken from the video processing. We're looking out into a field full of a mix of grass and stinging nettles, and we're trying to figure out where would be good places to spray with chemical. That's not necessarily the same place as the weeds themselves. In some cases, you're uncertain about whether something is a weed or grass. And so you've got to make a decision about what's the risk of spraying an area that is actually grass, if it's a weed or vice versa. Here's some video of that system in action. So if you're sitting on your computer at home while the robot is driving around outside, this is roughly what you'll see. So on the top left, we can see that the robot's eye view, we're out spotting dock leaves in this case, and we're trying to distinguish the dock leaves from the grass. We're again coloring them blue. Now in this case, we are just detecting. We're saying, is there a weed there or not? There's a separate process getting computed in the lower left, which is working out whether or not to actually spray them. And this is roughly what is called sensor fusion. Sensor fusion means you take several sources of information, such as several frames of the video, and you kind of average them together. You say, what is each of those images telling us about whether or not there's a weed there? And by combining information from several frames, that can include going away to another part of the field and then coming back and seeing the same weeds again. By combining all these different images, we can become more confident in whether or not there's a weed there. So the image here in the bottom left is a map of the field, and we're coloring this map in green and blue, depending on whether we think there are weeds, blue or green for grass. And this is taking individual frames as input and joining them together to increase the confidence down there. Let's take a look at some other applications. We were working on a dairy farm, so as well as looking at weeds, we tried replacing a few other agricultural activities, such as fetching the cows. So here's another manual process. 2 times a day you've got to go out and move the cows around. Could we replace that by automation? So here we're driving the vehicle around and we're seeing what the cows think of it. And we tended to find, as with many new things, as with many new things, the cows typically get interested in it for a while and try and play with it at first, and then you kind of jump on them and then they get scared, and then after that they realize that it's like a sheepdog, it's something that you're supposed to run away from rather than being interested in. So we had some success in herding the cows on this dairy farm as well. Okay, let's go back to my slides. I'll talk a little more about how the automation system works in Ibex. This system is used in some of the other robots as well. But roughly, we're using computer science algorithms to plan these swathing patterns. So in this case, we have a field. We're told we have to swathe it. We need to visit every location to check it for weeds. And we're saying what's the best way to drive up and down to ensure that you've covered everywhere without hitting anything, and preferably without traversing the same area more than once. This gets more interesting in highly three-dimensional terrains. So many of these dairy and sheep farms are on hills, and these hills can have slopes, often 30, 40 degree slopes. That's why they're used for dairy and sheep, because you can't drive, in some of the sheep farm cases, you can't drive large tractors around that would be needed for doing more profitable arable crops. So in this image, we're looking at a large three-dimensional terrain and trying to figure out how to plan around it. And an interesting change when you go to 3 dimensions is that many of the laws of geometry no longer work. You'll find that the angles in a triangle don't add up to 180 degrees anymore, for example. Many of the things you learn in school geometry don't apply in curved space. And indeed, this can quickly get you into the same kind of mathematics that Einstein was using in his theory of relativity, which is also dealing with, in that case, 3-dimensional curved space. We're only dealing with curvature in 2 dimensions, the hills and the valleys. Planning in this kind of environment can be very different from planning in a flat arable environment. Something else we have to deal with in practice is communications. Probably most of you are used to pulling out a mobile phone anywhere you go and assuming that you can just stream video over it without any problems. That is not the case in agricultural environments, which are often located far away from the nearest mobile phone transmitter. And even if they're near one, there may be obstacles in the way, restricting the signals. We really need to transmit video over that link. We need to see the weeds coming in. Typically, we want to do the clever AI work on a computer that isn't physically on the robot. It might be a long way away, somewhere over the internet. And transmitting video in real time is very different from streaming it over YouTube. Okay, so with YouTube, if you're watching a music video, say, YouTube can predict very well in advance what you will want to watch next. If you've started watching a video, YouTube knows that you're going to spend the next 3 minutes watching it, and it can spend that time getting all the video ready and sending it to you in advance over your connection, which can then play it back at the right speed. If you're transmitting live video, it's very different because you can't send anything in advance. You only have 1 frame at a time actually coming in, and you need to get that back to base as quickly as you can. So there's a lot of work in agricultural robotics that goes into communication systems for robots in the field. Okay, and these images show the history of how our systems evolved over time. We started off just using these gardeners boxes, putting a load of electronics and batteries and antennas in them, For a while, they were sat on a step ladder like this. And then when we figured out what we were doing, we got it into this much slicker structure shown on the right. This is a fully weatherproof system, and it's something that can easily be deployed, in this case by John, our radio expert. He's just pulled this out of a van and he's winding up a handle to set up that antenna out in the field. So often when you see videos of robots, it looks like the robot is the cool thing. You can understand the robot is a live agent that is driving around. Everyone wants to be an engineer and to build those robots, but what you don't see is all this stuff around the robot. To make that robot work, there's a lot of infrastructure. There's a lot of electronics and communications and radio signals. This stuff is just as important as building the physical robot itself. And there's probably going to be a lot of interesting research over the next years and decades into figuring out how to specialize this for agricultural application. We also play with drones. Here is a drone working together with the Ibex robot, and on the left is a map of a field that has been mapped out by a drone. So in this case, that drone has flown around in advance of the robot. It's trying to spot the weeds before the robot can get there. And that means that the robot then doesn't have to swathe up and down the entire field, because it already knows where the weeds are and it only has to go out and visit the weeds. So there's, again, lots of very interesting mathematics in how to do this efficiently and well. It's inefficient having the robot swathe the whole field, because the robot is a large, heavy chunk of metal, and it requires fuel, electricity, to make it go, whereas the drone is small and fast, and relatively cheap to run. So there's lots of different ways that the drone and the robot can work together. You might want to have the drone go out and spot the weeds entirely in advance, or you might want to only send the drone to places that the robot asks it to go. The robot may be driving around and it sees something that looks a bit like a weed while it's on the way to doing something else, and then you might want to go and send the drone to go and investigate it in more detail. So all of those ideas can be described by equations. You can effectively use calculus to do gradient descent and to find the most optimal solutions. And typically, you'll write down a set of equations saying what is the cost of the robots working in a certain way. And then you want to say what is d cost by d parameters. The parameters describe what the robots are going to do. That gives you a gradient, and then you follow that gradient and you minimize it. And that's called optimization. So, yes, calculus is useful in the real world. We use it every day for these kinds of optimization problems. Okay, that's IBEX. Let's take a look at another project. This one is called ARWAC, which stands for Autonomous Robot for Weeding Arable Crops. And this is a system that is more suited to Lincolnshire style agriculture, which is primarily arable and is usually very big. Sheep and dairy farms are often small family farms in the north of England. When you come down here, this is agribusiness. Everything is scaled up. So these arable farms currently have a problem. They're often growing wheat, and wheat has been infested by this horrible weed known as blackgrass. And blackgrass is very difficult to control because it is a grass. And the thing about wheat is that it is a grass. Okay, wheat is just one type of grass which has evolved in a particular way to be especially nutritious for humans. It is a member of the grass family. There are many different grasses. There isn't a single plant called grass. Lots of plants are called grasses. And wheat is a grass and blackgrass is a grass. And the problem is you've got grass growing mixed up with grass, and you're trying to tell the difference. So if you take a look at this image, this is rows of wheat growing in Lincolnshire. And somewhere in this image is a load of blackgrass. Okay, the blackgrass is mixed up with the wheat, and we'd like to kill the blackgrass without killing the wheat. So many problems with this. You can try and do the selective herbicide approach. Remember, that means using chemistry to create herbicides which only kill the weed and don't kill the crop. The problem with that is that the weed and the crop are both grass, and they're both very closely related. And so all the chemicals we've tried will either kill both of them or neither of them. It's very hard to separate wheat and blackgrass using a chemical method. You might try and do this visually. That was easy in the case of the stinging nettles and the dock leaves. It's quite hard, you will find, as a human, to actually tell the difference between the wheat and the grass there. Most people think of wheat as being yellow. Okay, wheat goes yellow when it's ready to harvest. That happens at the end of its growth. By the time that's happened, it's too late. Okay, what you're trying to do is control the weeds before the crop is ready. You're trying to control the weeds while the crop is growing, and this is what wheat looks like earlier in its life cycle. This is where weed control is most important, when it's still green. So again, we've been out in fields, we've been trying various mechanical systems for control, and this early prototype, this was called Teresa because it runs through fields of wheat, like our former Prime Minister. The idea here is we're going to take a bunch of mechanical hose, a bit like a giant comb or a giant fork, and we're going to pull those through the rows in a way that doesn't disturb the wheat. We're going to try and get these metal spikes or tines so that they're lined up in between the rows of the wheat. And then when we drive the thing forward, that's going to pull up all the soil in between the rows, destroying the blackgrass, and it's going to leave the wheat alone. And we don't want to do that in the whole field. We only want to do that in areas, again, spotted by a drone, which are known to be infested with blackgrass. So again, we're going to fly a drone over the field first. We are going to use what is called hyperspectral imaging to find the patches of weeds. So human eyes can see red, green, and blue. Other creatures, like insects, can see some other colors as well. And similar to those insects, there are robotic systems which can see these other frequencies. And some of those colors, not visible to humans, contain useful information about the difference between the blackgrass and the wheat. They do have somewhat different chemistry, but it only shows up in the colors that humans can't see, but our drones can. This shows a later version of the robot. And on the right, we're showing a concept for following the rows. We need to make sure those hose get put in the right place so they don't disturb the crop. And so here we're looking for rows, straight lines of green stuff, and we're comparing it with the background, which is brown soil. This algorithm is developed by one of our researchers called Don Lee. It's been through many iterations and can just about guide the robot to drive down rows of wheat without hitting the crop. So let's take a look at some video showing Don's algorithm in action. So as with the grassland crops, this algorithm has several stages. What you're seeing here is one of the earlier stages. The lines here are suggestions, and they're just suggestions at this stage about the positions of the crop rows. And these suggestions come from looking at the brown and the green and trying to group the green into areas that are straight lines. So as with the grassland weeds, we can continue to process this. We can make use of other sources of information that we have. That includes fusing many frames of video together. We might have other information in advance. So some farmers have GPS on their tractors, which stores information about where the crop was planted in the first place. and so on. We try and fuse all that information together to make a decision about where the rows are. I see James Brown says, yay for the Hough transform. That's exactly one of the algorithms getting used in there. Good. Okay. Just show you this. This is the latest evolution on the mechanical side. So usually in these projects, we have software people like Dom working on the algorithms. I should mention Jonathan Cox as well, who's doing the algorithms for the drone recognition. We also have mechanical engineers working on what is called metal bashing by the software people, coming up with better and better ways to create the physical platform. So you can see it's evolved over time to become more robust. The wheel geometry has been moved around. We've switched from what is called skid steering. So skid steering means the wheels don't turn left and right. Instead, you have the wheels on the left side of the robot going at a different speed from the ones on the right-hand side of the robot, like a tank. That creates what is called differential drive to steer. Whereas the new version here on the right is more like a car. That steering system is called Ackermann steering. That means you actually rotate the wheels left and right to decide which way you want to go. Okay, let's look at a third final project called LaserBoom, and this is applying more robotics ideas, but in this case to larger tractors. So ideally, we'd like to get away from agriculture altogether and do horticulture. But in some cases, the way the real world works is very based around these big tractors. People will just laugh at you if you do things with a small robot. And in those cases, you have to work with the existing system. If people are already using a big tractor like this one, you're going to have to lump it and just help to optimize what is actually there. So the reality of these large arable fields is lots of spraying from very large boom sprayers. These could be 20, 30 meters across, being driven by a tractor with a human driver. And again, the reason they've got so large is purely down to the labor cost of paying people to drive the tractors. You can pay the same driver the same amount of money to drive one great big tractor and cover the field in 10 minutes rather than 10 people driving 10 small tractors. The problem with this system is a classic agriculture problem. Remember, agriculture means aggregation, and it means treating everything the same. And in this case, that means bulk spraying the whole field with this chemical. We would like to at least be able to apply the chemical in a consistent way, so the same amount of it lands at each location. But we can't do that because the booms bounce around. Real fields are not completely flat. The tractor drives over relatively small bumps in an agricultural field, but because of the geometry of the system, a small bump driven over by the tractor can produce a very large wobble at the end of the boom. So the end of the boom may be moving a meter up and down. And if the boom moves up a meter, that means the spray is fired from a higher position, and that means more of it goes into the wind and blows around and gets lost and probably ends up in the water supply. So what we'd like to do in this case is control the boom. We'd like to monitor where it is, how it is wobbling around, and consider it as a large robot arm and use all the same mathematics, engineering systems that we'd use in a robot arm to manipulate the position of this boom so that we can normalize the amount of pesticide landing on the crop. So we do this using the same laser scanners that we saw on the IVEX robot, again called LiDAR, and IMU, inertial measurement unit. That gives us some idea of how the tractor is bouncing around, how it's rotating in response to going over bumps in the field. The image on the right shows what is called a point cloud. That's all the data we get from a LiDAR sensor. It's showing little dots in 3D, which together form the shape of the canopy of the crop. Canopy is the surface formed by the top of each plant. And by using LiDAR, we can look ahead. We can look maybe 20 meters up ahead, build up a map of what we think the surface is going to do, how it moves up and down. And in response to that, we again use calculus. We're going to say what is D cost by D parameter to try and minimize the cost. We're going to find a way to get that arm into the optimal position over time to make the chemical spray applied in the best way that we can. This has been a nice example of how blue sky research translates into practice. So some science is paid for by the government because they want a particular problem to be solved. So in this case, the problem of spraying chemicals on wheat is an urgent problem to be solved. And it's an obvious thing for a government to go and give someone money to do that. What you find is that when you try and solve these problems, you will generally need to get your ideas from more abstract blue sky research that's been done first. And in this case, we were able to look back at research from about 10 years ago on rats and whiskers and touch perception. So these images here on the right show two robots that are built mimicking the whiskers of a rat. This work was funded by the European Union rather than by the UK. And rather than solving a problem, it was intended to explore the idea of whiskers and how rats behave. We looked at rat psychology, rat biology, and then those ideas were translated into what would happen if we build a robot using the same ideas. But through that whole process, there was no application in mind. It was science for its own sake, to understand what is a whisker, how the whiskers bend, and how the whiskers can be controlled. If you know how the whiskers bend and vibrate, you can figure out how to actively control them at their bases to get them into places where you want. And this is, in fact, a very similar process to what is needed in the agricultural application. We know that that giant 30-meter boom is vibrating around, somewhat like a musical instrument. If you've ever seen a video of someone hitting a tuning fork, for example, you'll see the same kinds of vibrations. We can use the same mathematics, which is called Bernoulli-Euler beam theory, usually used by civil engineers for building bridges and stuff. But that mathematics was developed into a model of vibrating whiskers in the blue sky research. And from there, it can come into agricultural control to solve the problem. So very often, if you want to solve a practical problem, you first have to do the basic research. You have to make sure that that is taking place and that it is available. And then when people come to solve the practical problem, they need access to it. And that's their source of ideas for their immediate problem. I'll just talk a little bit about things we'd like to do next here at Lincoln. Generally, the move is away from agriculture to horticulture, and horticulture means per plant precision. It means treating each plant as an individual, like a human gardener would. And that means monitoring, planting, fertilizing, watering, harvesting. Agricultural industry is making some progress towards this, usually not at a per plant level, but we're seeing what is called precision agriculture, typically mapping out fields to a resolution of around a meter, like in this image. So you might say this meter square of a field has a certain chemical balance, or this meter squared is short of water, go and put some water there. That exists in industry currently, and we're trying to increase the resolution to get it all the way down to single plants. Again, here's some images coming from those LiDAR sensors. Those are the laser scanners. We're building up a 3D map of rows of crops and trying to identify the structure of individual plants within that. There's a lot of artificial intelligence, machine vision, machine learning goes into that transformation from just a set of dots in 3D space to saying this is one plant, and deciding that a bunch of dots are all parts of the same plant. The big picture is agriculture is still just one component of the food system. Remember, there are other losses of food in the system all along the supply chain. And with our colleagues in food technology, food engineering, and our colleagues in transport studies, transport engineering, and product design, we are increasingly working together to think about how to optimize the supply chain as a whole. So this is how the food system might look in 20 years' time if everything actually works. We might see robots in the field here on the top left harvesting individual items of fruit. Okay, this is a robot arm picking a pepper. So that pepper will be put in a box in the field with a bunch of other peppers. They will be taken to a factory. There may be other robot arms in the factory that sort them out. Currently, we use humans in the factories. They're looking at the individual peppers, inspecting them, checking them for defects, throwing away the bad ones, and putting them into a nice little punnet or wrapper that can be sent for a consumer to buy in a supermarket. That's going to be sent there in a truck. A truck is a form of transportation system. There are many optimizations that AI, machine learning, data science are working on in transport studies. This can include everything from the locations of the deliveries, the locations of warehouses. A supermarket like Tesco will have several warehouses around the country, and food is taken from a farm to a warehouse, sometimes moved between the warehouses, ultimately to a supermarket. And there's a lot of mathematical optimization, again, lots of calculus, lots of minimization of cost, trying to figure out where you should put the warehouses, where you should build the roads, the motorways, how you should deploy your trucks to move things around in the optimal way. We've worked a little bit with local councils talking about their transport infrastructure. So here on the bottom left are some traffic lights. Increasingly, infrastructure such as traffic lights is all connected to the internet now. That means it can be controlled, it can be monitored, and you can shape the flow of traffic around the network in response to what is actually happening. So for example, if a truck full of fresh strawberries is arriving, and in the other way there's a truck full of Nintendo Switches, you might choose to prioritize the strawberries because they're fresh. Okay, they really need to get to the supermarket and to the customers quickly, whereas the Nintendo Switches can possibly wait a few days. And if all of that information is in databases connected to the internet, you can ultimately calculate the most effective route for it to move through the traffic and shape it with things like traffic light behavior. So you could have all the traffic lights in London turning green to let the truck of strawberries get through the traffic like an ambulance as quickly as possible. A lot of this data is already being collected at the consumer end. So here's someone with a supermarket reward card. Most customers are happy to hand over all their personal information on these reward cards in exchange for a few pounds of free stuff at Christmas. When you're doing that, you're giving over very detailed information, not just about what you've bought, but ultimately about who you are, your lifestyle, your interests, your hobbies. Your supermarket can figure out what kind of relationships you have, how your life is changing, where you're going, who you're with, all kinds of things from that data. And there are some quite malicious uses of that data, but there are also good uses of it, such as feeding into the supply chain to optimize everything else that is going on. Now, that can include scheduling the transport. It can include decisions about what food should be grown in the future, what do people actually want. Increasingly, that intelligence is going to keep going closer to the consumer. You might have a smart fridge pretty soon. some versions of this already exist. We're going to see more computers in your fridge that are monitoring what is in there, figuring out when you need more stuff, eventually ordering it automatically. When you run out of milk, your fridge will see that coming and it will place an order with Tesco. And maybe that order will also be delivered by a robot, such as this autonomous last mile delivery platform on the bottom right. So the last mile means getting from the supermarket to the consumer's house, and it's traditionally been the hardest part of the supply chain to optimize. So we have another project running at Lincoln right now called Autonomous Delivery Vehicles, which is researching exactly this. If you come to Lincoln campus next year, you'll probably see something very similar to this running around on our campus as we test that last mile delivery automation. Maybe we'll get it to deliver sandwiches to the university canteens or something as a test. So that's an overview of just some of the work we do at Lincoln. We're a big research centre. There are many other projects, many other people involved in all of this. I thought I'd finish just by talking about what happens after the university. How do we get these systems from a science lab into the real world of farms and supermarkets? Britain has traditionally not been very good at doing this, especially compared to the Americans. Britain has a tradition of inventing really good ideas and then having the Americans nick them all and make all the money. And there's a lot of interest in Britain now in how we should do this more effectively. The problem is often called the Valley of Death. It means ideas sit in the university and somehow they have to cross over into industry. That means people need to invest in it. Usually to get to industry, you need to spend more money. And the people who funded you to do science and paid you to be a scientist don't want to pay you to take it out for someone else to get rich off in a company. But at the same time, the companies don't want to pay you either because they think it's too risky. It's not been tried and tested. Every company would rather have some other company investigate it first, and then the minute they see it working, they'll jump on it and invest in it themselves. But nobody ever wants to be the first to invest in that. So there's a lot of discussion in the UK and in Lincoln in particular in how this could be done more effectively. Roughly in Lincoln, we find ourselves not just sitting in an ivory tower thinking about AI theory all day. We find ourselves going out and working with what are called consortiums, large groups of organizations. And some of those are partners. Some of those are people who do science and engineering that we can't do. Every university has its own specialisms. We specialize a lot in these kinds of agricultural robotics. Sometimes we need expertise from outside. Those people have to come in. Sometimes we need commercial expertise, people who know how to create a company and sell things. Selling is a very different skill from doing science. And we need investors. We need rich people to come and let us use their money for a while to try and build something out of a lab into something that is actually going to get taken up outside. It's about how you cross the Valley of Death. And all of this is powered by our students. Students come, they study at undergraduate level to learn the basics of this. They'll go and work for all these companies. Our students will take the ideas out as employees. They get nice jobs. They build stuff. They make it really work. You can come and do an MSc. That's a higher degree. You can do that after your BSc. That's where you can really specialize in particular fields of robotics. Some of them stay all the way on, like I did, to do a PhD. That makes you a doctor. Typically, the people with PhDs will be on the cutting edge of research and choosing which ideas actually get taken out into the real world. So if anyone's interested in collaborating with us in any of these ways, if you're involved in agriculture or your friends or family are involved in automation, engineering, machinery, or if you're really rich and would like to invest some money, please do get in contact. Or if you're a student and you'd like to come and learn to do this yourselves, please come to Lincoln and do that. Thank you. Any questions? Do we have any questions? You can type your question in the public comments, I think. Message from Naomi. Doesn't seem to be any questions, so we can wrap up. Okay, if anyone has any follow-up questions, please feel free to send me an email. I'm Dr. Charles Fox. You can find me at the University of Lincoln using the internet. Usually happy to respond to any interesting questions you might have. Thanks for listening. Bye-bye.